We're going to start talking about transistors in this clip, and this is really a review subject because transistors are something that I think most of you have gone over already in second year, and I'm going to review it simply because transistors are very important. Your understanding of transistors will help you a lot with understanding how SCRs work. And so before we go ahead into SCRs, we definitely need to give some review time to transistors. So I'm going to go ahead and I'm going to do a little bit of a diagram here and just remind you of the types of configurations that we have with transistors. So to begin with, we have two different configurations that are possible in the layering of the semiconductor material. We can have N on the outside, P in the middle, and N on the other side, or we can have kind of the inverse of that, which is P on the outside, N in the middle, and then P on the outside. Now, a lot of times people ask, well, really, what's the difference? There's not very much difference, but there are a couple of things. And so let me just go ahead. First, I'm going to show you the symbol. Here we have the base. This is the collector. And here we have the emitter. And on an NPN, our little diode arrow, indicating arrow, they don't show it on these symbols, but it really is like this. It's essentially a PN junction, this being the N-type material, this being the P-type material. Okay, so what happens here is really, it looks like this. I'll just draw over this. You can see it's a piece of material there, piece of material there, and a piece of material there. Lead here, and a lead here. And the collector is connected to N-type, the base is connected to P-type, and the emitter is to the N-type again, okay? So that's the way that one goes. Now, let's talk about current flow in an NPN. Current flow is, we look at I of C being the load current, and it comes down, goes through the transistor, and it goes out, and down here we call it I of E. Now the only thing that happens is we have base current that flows in, I of B, goes through that material, and it joins onto that current. So I of C plus I of B equal I of E. Now let's take a look at what happens in the PNP. Here we have the base. All right, and the collector and the emitter. And here we have an arrow that points in. Okay, so that's one of the differences there. The arrow shown is in the opposite direction for a PNP. The other thing that happens though is when these are connected in a circuit, they're actually connected a little differently, and the current actually comes in to the emitter. So I of E comes in, it goes through, and then it goes out as I of C. And what happens is some of that current splits off as it goes through the transistor, and it goes out as I of B, but flowing out of the base instead of into the base. So here's I of B, okay? So it's really just a difference in the polarity and the hookup. But the other difference is this. Here's the layers, right? This is now the collector connected to P-type. The emitter collected is also to P-type, and the base to N-type. Here's the difference. With an NPN, as base current if base current is cut off or at zero, then the collector current is also cut off. And as base current rises, collector current also rises. In a PNP, when the base current is cut off, you will have the maximum current at I of C. But as the current flowing through the base increases, then the collector current will fall off. When you get to your saturation level current on your base, I of C will be cut off. There'll be nothing flowing out I of C. So it's very similar to looking at something like a contact. We have contacts, you know, we're used to looking at these. This contact we would say is normally open when de-energized. So it's open when de-energized, and then it closes when you energize. Whereas this one is closed when it's de-energized, and then opens when you energize. And it's a similar idea. You would use these devices. You would choose your transistor based on your application and whether you needed to have full current with full signal or no current with full signal. So it really depends on your application which one you use. Now, the other thing that we typically call these, they're referred to as BJTs, which is bipolar junction transistor. Bipolar junction transistor. And what we want to do is I want to talk a little bit about testing these. One of the things that will come up is definitely how we can use an ohmmeter to test them. So give me a moment. I'm just going to redraw this, and then we're going to carry on, and I'll explain that to you. All right. The next thing then, ohmmeter test, looks a little bit like this. If you think about the layers in a transistor, we just looked at that. We said we have NPN and PNP, and you know, if we have just a PN layer, we know that that looks like a diode. And so the way that I like to draw this for testing is like this. I put the base in the middle, and I'll put the emitter over here, and then we know that if, you know, when we have an NPN, that the actual symbol goes in this direction on here, right? Just like that, towards the emitter. And that's really just like a diode symbol, and that really applies to this, okay? Now the part that is not really drawn like this all the time, but what do you think the symbol looks like, you know, for this piece here? Well, it's exactly the opposite, because now you have the P-type material here and the N-type material over here. So this is like a junction going this way. And here you got the collector. So really you can just view it as two diodes that are inverse connected. And if you take an ohmmeter and do a little testing on this, this is what you would typically get. So let's take and we'll put an ohmmeter like this. I'm going to use the negative. This will be the negative lead on the ohmmeter, and this will be the positive lead on the ohmmeter. Now we know that if you're going to take your meter and you want to test any of these points, forward biased means putting the negative lead on the N-type material. Now this is the N-type material over here, and P-type material in the middle. So let's start with this. I'm going to list these down kind of in the same way. This will be the emitter and the collector. These will be the two test points, okay? Then we'll do the opposite, collector to emitter. Then we'll do the emitter to the base. Then we'll do the base to the emitter. Then we'll do the collector to the base, and the base to the collector. Now in each of these cases, we're going to get a reading. Either it's going to be a very low reading, you know, a very, very small amount of resistance, and that's what we'll have if it's forward biased. And typically says OL if we reverse biased and it's in good shape, and that means open lead. So in other words, no circuit there. It's like you've taken a lead right off. OL. So let's double check our points, okay? So negative, positive. So if we put negative here and positive here, what's going to get through this arrangement of two diodes back to back? Absolutely nothing. And so this is going to be OL, okay? What about if we go from C to E? Well, guess what? Because either way, so here we put negative and positive, either way you look at this, one of them is going to block. And so that is also OL. Now, if we go E to B, so we put negative here and positive here, this is going to be low. We're going to get a low reading. What about if we go the other direction, B to E? That means putting the negative here and the positive here. And as you can see, that now is actually reverse biased. And reverse biased will mean an OL. Okay, now what about collector to base? Negative, positive. Remember, this is the N-type material, and so that will actually be a low reading. Okay, and if we go and we put the negative on the P-type material and the positive on the N-type material, now we're reverse biased, and you will see OL again. Okay. Now, as you can imagine, the PNP is going to look like this. We're still going to have the emitter, but now we're going to have this. And here's the base. And there's the collector. So this is the way to think of it. It's really just a very kind of a straightforward looking thing. We'll use the same meter positions, and we'll go E, C. We'll keep the arrangement the same. Okay, C, E, C to E, E to B, and B to E. Sorry, C, 1, 2, 3, B to E. C to B, and B to C. All right, now let's take a look and see what happens here. First of all, as long as this transistor is in good condition, let's take a look at these. This reading won't change because that's the same on either one. We've got one will conduct and one will block. So these first two have to be OL. Okay, open lead. Now let's look at this for a moment. If we put the meter leads on in the same set of configurations as we did here, just like we've shown, but these two NPNs have become PNs, so this NP became a PN and this NP to P became a P to N, then what's going to happen is these two are just going to flip. So in other words, E to B is going to be an OL. E to B. So if you put the negative lead on E and the positive lead on B, instead of getting a low reading, now we're going to get a high reading. So it's going to be OL, OL. So that one was low, now it's going to be OL. This one was OL, now it'll be low. This one was low, now it'll be OL. This one was OL, now it will be low. Okay, so that just shows you, what the readings should be. Now, what are the conditions that can happen? Why do we want to test these transistors, right? Well, there's two things that can happen. The transistor, typically the C to E, that main current path, can become open or it can become shorted. Now, there are some other problems that could occur with the base, but very, very often it is a matter of either shorted or open. So let's talk about both of those. Here's what shorted would look like, okay? Shorted would essentially give you, and it could be on either side, but it's really just a situation where this line becomes like that. Okay, there's no more diode action in there. It's just literally shorted. And so you're going to get a different set of readings than you would. For instance, if you put on this particular arrangement, if this side was shorted and you put negative on here and positive there, you would get a, that would be an OL, okay? You would get an OL, open lead, because it would block here. But remember, if everything's in good shape, we should have OL on both of those. If you put the negative here, you would get a low reading, and you would know, okay, that thing's actually supposed to be a high reading, and so it's shorted. So once you know, these are kind of the lists of, these are the correct readings for a transistor that's working order. If you get different readings, you can actually determine whether it's shorted or whether it's open. So if you get nothing in a place where you should have a low reading, then you know that it's actually open. You get OL and it's supposed to be low. You got a transistor that's buggered because it's actually open. All right. So gives you a little bit of an idea on how to lay that out and do a determination on what kind of condition your transistor is in. Okay, I'm just going to clear this off, and we're going to start to take a little look at some of the applications. What do we use these transistors for? Now, transistors have essentially kind of two different main application type purposes, I guess I would say. But what we're going to do is I'm going to give you, first of all, I want to talk about transistor states. Transistor states. And what that means is essentially this. I'm going to show you a little graph, and this is going to be collector current. Collector current. And over here, I'm going to show on this line, I'm going to show base current. Now, just by way of reminder, base current and collector current are very, very closely related to each other by a specific ratio that we call gain. Okay, and it's a ratio. And this ratio is I of C, and it's between I of C and I of B. So the base and collector current always operate in a very specific ratio to each other. So I'm going to talk about an NPN in this example, but you could very easily apply this to a PNP. The line would just go in a little bit of a different direction. But I'm going to show you an NPN, and here's what it looks like. If we take this line right here and we say that that is the maximum collector current that this transistor is rated for, and then I make a line across like this, and I'm going to make a line down here, and let's say that it takes this much base current. So this is I of B, and this is I of C. So there's my maximum I of C that I'm rated for, and this is the maximum base current. And because this current increases and this current increases in an exact ratio to it, that means that as my base current increases, the line would look like this. So as my base current goes higher and higher in this direction, as my base current goes higher, my I of C goes higher. And so what we do is we say, well, so the transistor really has three states. When there's no base current, we call this state cutoff. That's cutoff. When there's no base current and there is no collector current, we say that the transistor is cut off. When we reach our level of base current, that will exactly bring us to the maximum collector current, we say that it is saturated. Saturated. Okay, so our first state is cutoff. Our second state is saturated. Now, what about everything in between? Well, what happens is that if we reach a level of about 50% on our base current, then we'll be at a level of about 50% on our collector current. So this is where, in this region, anywhere in between cutoff and saturation is a section that is it's linear, and we call it active. Okay, the transistor is active, which means that it's somewhere between. Now, the applications for transistors are kind of like this. Well, we use them, first of all, as a very fast-acting switch. Okay, that's the first application. And the second application, well, we use them as amplifiers. An amplifier to take in a certain amount of signal, which would come in on the base, and then that amplifies that to a very specific larger amount of current that would flow in the collector. Now, as a switch, okay, the only thing we're concerned about is where's cutoff and where's saturation. So as a switch, we use it between these two states. It's either cut off or it's saturated. One of the two, okay? It's either cut off or it's saturated. Now, if we go to use the same transistor, but we want to use it as an amplifier, then we're simply using it in its active state. In other words, we're gonna put in that base signal to some point, and we're gonna see how much collector we have. And so we're really using it in its active or its linear state. So just to realize, many cases, of course, it's used as a switch. I guess I would say as an amplifier, it tends to be more in audio type applications. But you can definitely use it. There are many applications even in the more electrical related electronics where it can be used as an amplifier. So both applications are something that we should be aware of. All right. Now, as I said before, if this was a PNP, then what we would be looking at is this line. Instead of going at 0 base current up here, it would actually start here and it would come down here, meaning that with a PNP transistor, when you get to your maximum saturation point base current, you would actually be at your collector current would be at 0. So it actually kind of goes the opposite direction, right? So that's just for you to understand. It's not something, of course, that we can become too detailed about. Now, the next thing I need to do is I need to make a fairly extensive list of transistor ratings that are important. When we choose transistors, there are a few considerations that we have to look into in terms of whether they're going to be adequate for the circuit that we're building. And so we're going to consult with a spec sheet, and there's a few key things that we want to identify. And so these specs are important. First thing up here we have is the I of the C, which is the collector current. So this is going to be a rating usually in amps. This is the load current flows through the collector. So what is the total amount of amps that can flow through this transistor? And so, you know, that's going to be something that'll be a careful consideration when you're building a circuit. Now, VCE, the collector to emitter voltage. And so this is an important one because depending on the voltage of the supply, you know, some sources actually have a fairly high peak voltage. And so if you're going to use this as a switch, it has to be able to block against some level of peak voltage. And so that collector to emitter voltage is an important voltage rating that you need to pay attention to. Now, the amount of power. This is the power dissipated by the circuit. So there's definitely going to be some power dissipated, and we need to know what the maximum power is that it can handle. And so we want that to be rated in watts. Now, I of B, that is the base current. So we want to consider base current. Usually a very, very small amount, and but also rated in amps, probably going to be in the milliamps, so a very, very small value. Important factor is the designed gain. Okay, now we know that transistors work on a ratio basis between their two currents. This current, which is your collector, and this current, which is your base, and these are in a relationship, a ratio relationship, and we call this their gain. And it's a very specific design ratio. It's the way that the semiconductor layers are doped that determines exactly what that ratio will be. So the gain of the transistor is an important part of the specs. Now, temperature. Now we know that, and we'd mentioned this before, that temperature, very, very important with electronic components. Heat is the enemy. If they get too hot, their performance will definitely suffer. And so this temperature rating in degrees will just typically they'll show it in Celsius and Fahrenheit. And it's, if you get higher than that, probably the results are going to be pretty poor. All right. Frequency. We know that in many cases we use these for switching. And so there's two sort of separate parts to this. First of all, there's the frequency that they can manage. So whether it's in hundreds or thousands or millions of hertz that it can actually switch per second, that would be its frequency. But we also have switching time. And so really they're related, because the slower the switching time is, then the slower the overall frequency will be. So they are related, but they show the frequency and the switching time. Switching time usually in microseconds, or even down into even smaller units in some transistors. So that gives you a little bit of an idea. Now, I am going to place a PDF that's going to be available for you, along with the other spec and data sheets that I'm putting for the other components. I'm going to place a couple for transistors for you to basically peruse and look at and be familiar with. So those will be available also. In order to understand how a transistor circuit really works, and how to understand the values in there and be able to calculate them, there's a few terms that we need to be aware of. I'm going to start over here with the source. And the source in a transistor circuit we call VCC, which actually means the voltage from the collector to the collector. So in other words, what is the voltage all the way around the circuit? So VCC is our source voltage. Now I'm going to move along like this, and I'm going to show you how I would typically draw these out, and just an convenient way of looking at them. All right. If we look at it in this way, I normally put the load up here. Okay, that would be the load. And we essentially, we call the voltage across the load, it's essentially a drop. We call it VRL, which is the voltage across the resistance of the load, so VRL. And then we move down, and I'm going to draw this transistor a little bit differently, in that I'm just going to show its layers like this. I'm going to use an NPN like that. Now, out of this end, we have the emitter connected to the N-type material on the bottom there. So if this voltage here is essentially VRL, if you look at VCC, and I'm going to put some numbers on here just so you can make sense out of this. Let's say this was 10 volts DC, and I'm going to put a random number here, and I'm going to say this is 6 volts. We know that this branch really, I can see this line and this line here both connect right to the source. So I have to drop 10 volts. And so what we have here is what we call VCC. CE, which is V collector to emitter. And as you recall, that is one of the ratings, the maximum voltage drop collector to emitter of a transistor. And so this one, in this case, would be 4 volts because it has to equal 10 volts total. They're in series with each other. Now, we do have one more branch in this circuit, which is actually parallel with this branch here. So this here we could call the load branch, and this is the kind of the base branch. Okay, so let's take a look. Here we've got a resistor like this, and from there, this resistor, of course, is to limit the base current. Base currents are typically very, very small values because they're, just a fraction of what the current through the collector will be. And here we have the base right here. So this current enters to the base. Now, what I want you to see is that if I'm gonna give you this by states, okay? If this is cut off, it would be like us having a switch in here, okay? If this is cut off, which means we have no base current, then there would be no voltage dropped here and no voltage dropped here because there would be no current there. And so in the cutoff state, all we have is, essentially whatever's going on over here. And by the way, when it's cut off, we would actually, I'm going to alter these values just so you can see it. When it's cut off like this would actually be 0 volts, and this would be 10 volts, okay? That's cut off. That's our cutoff position. Now, as soon as we close this switch, let's say I'm set up with a resistor in here that that gives me, roughly about just enough current to take us back where we were at 6 volts and 4 volts here. Okay, so we're not at saturation. Of course, we're not at cutoff. We are in our active or our linear state. And so let's take a look at what we would say now. We would say, well, we have voltage across this resistor. So we call this V of the resistor of the base, or VRB. And this voltage also is in series with the voltage of this junction. See, we've got a junction that we have to cross there. And this voltage is 0.7 of a volt, and we call it VBE, and it's 0.7. And so the nice thing about this is as long as a circuit is in its conducting state, somewhere in the active range, what we do know is this voltage is very easy to calculate because as soon as we pass 0.7 of a volt here, we get some current flowing. Then what we have is, this is always 0.7, this is the balance. So this is always 9. As long as we're not cut off, this is 9.3 volts. So it's very easy to do calculations based on that resistance, all right? So how would I simplify this? I would just say that in any time that you have, when you look at a transistor circuit, you're looking at 2 branches with 2 voltages each. So here you've got VRB and VBE in series, and here you got VRL and VCE in series. Both of those branches here, so this is in series here, and they're in parallel with each other, and VCC is equal to them. So basically it's 2 parallel branches across your source. And so it makes it actually quite straightforward in terms of calculating the values in the circuit if you can see it like that. Kirchhoff's current law is one of the things that's very important when you're looking at this. The current in this branch we always look at, we call I of the base. The current that enters the collector, I of C, and the current that leaves the emitter, I of E. And in an NPN, I'll give you the values for an NPN, the relationships I should say. NPN, what we can say is that I of E is equal to I of B plus I of C. So there's your first relationship. I of E equals I of B plus I of C. Now what about the collector? Well, I of C is equal to I of E minus I of B. And what about our base current? Well, we can say I of B is actually equal to I of E minus I of C. And so you can always work it out that way using Kirchhoff's current law. So those are kind of the three current relationships that we should be aware of. Now, I of C and I of B, these two always closely related. I always like to put a little thing there. That's my gain, okay? There's the relationship between those two currents. Okay, nice little circuit here. We have a source voltage of 30 volts. We have a transistor that is an NPN. And I'll put the symbol on here just so you can see that. Here's the symbol that shows you that it's actually an NPN. Now, I showed you just recently how to calculate the values. There's really two parallel branches, and so let's take a look. What we want to know is what resistance on this base resistor will bring this transistor to saturation. Now, saturation we said was when we have the maximum amount of possible current, through our load. Now, what is the maximum possible current through the load? And here's how we actually figure it out. Now, let me start by explaining it like this. If base current flows into the base, and as that current increases, this load current increases, at some point, the current across here will almost give us a voltage drop across here of 30 volts. But it can never quite get to 30 volts, and here's the reason. Even when we're at our maximum conduction rate through the transistor, the lowest possible collector to emitter voltage is actually 0.1 of a volt. So VCE equals 0.1 of a volt when it's saturated. So when you're at saturation, VCE equals 0.1 of a volt. 0.1 of a volt. Now, that means that the voltage across the load at that point would be 29.9 volts, okay? 29.9 volts. So it's always a play. Remember, that's a series branch. We call it the load branch. And so really, if your lowest, fully conducting voltage across the transistor is 0.1 of a volt, then that leaves the 29.9 there. And that means that I now have an absolute maximum amount of current, okay? And that will be what we call IC, and that will be based on essentially the 29.9 volts and the 60 ohms. And I'm gonna quickly grab a calculator and I'm gonna run that through. So if my calculations are correct, that gives me a collector current, which is really the load current flowing into here, of 49.8 milliamps. Okay, so just a little less than 498 milliamps. My bad, 498 milliamps. So right about half an amp, right? About half an amp. Now, if I divide that by 100, which is the gain, right here, we're stated the ratio there, and this brings us down to 4.98 milliamps in here. 4.98 milliamps. 4.98 milliamps in my base circuit. Now, if I knew the actual voltage in my base across that base resistor, then I would actually be able to find the size of the resistance, no problem. And the truth is I do actually know, because I've got this very constant relationship, which is this is 0.7 of a volt. And so that means this is 29.3. So when I get to this point, I look at it, I've got 29.3 volts, 4.98 milliamps. And if I divide that out, I see that I have 5,884 ohms, 5,884. So this is 5,884 ohms, okay? And that is the actual size of the base resistance that I need to limit the base current to that exact value. Now that is the actual saturation current required. In other words, when I get up to 4.98 milliamps, it's saturated. And so what we, really what it amounts to is, if I was going to use this as a switch, it would operate between cutoff, which would be no base current, and probably sometimes they'll make it a little more. It might be just slightly higher, say about 525 milliamps or something like that, just to make sure it brings it to saturation. But you don't want to go very much higher. So a little bit more base current won't affect that. It'll bring it up. 29.9 volts is the maximum voltage that the load can have. And why is that? Well, look at your source voltage and the fact that you're going to have a 0.1 volt drop on VCE, and you know that you're never going to have a load voltage higher than 29.9 volts. And so that's what we call the saturation point. Okay, let's walk our way through this example. Now, as often happens, we do one or two examples one way, and then we say, well, let's look at what if we had different variables and we knew a different bit of information about it. Would we still be able to solve it? No problem, just based on the principles. So here we have we have a VCC source voltage, 32 volts. The beta of this transistor looks like an NPN, has a beta of 120 times. But we know that we have a base resistance of 85.7 k ohms. And the question that I see with this particular example is, what is the load resistance? How much load resistance is there? So we know that we're at the saturation point in this particular problem. And so there's a couple of things that we can place in. When we're at the saturation point, we know that the voltage from B to E is 0.7 of a volt. Okay, that's B to E. And at saturation, C to E, which I would show here, so this is BE, and CE is 0.1. So those are a couple of values that we know about the transistor at saturation, and so it's good for us to just put those in to begin with. Now, the 0.7 of a volt is in series with this base resistor, and the 0.1 of a volt is in series with this load resistor. So we can actually fill these in as well. This is going to be 31.9 volts, and this is going to be 31.3 volts. So now we literally know the 4 voltages, 2 in each branch, and it really becomes a matter now of doing some current calculations. So there's only one that we have enough information to actually calculate, and it is it's the base current. So if we want I is E over R, so we're going to go 31.3 volts divided by 85,700, and that gives us, looks to me like 0.365 of a milliamp. 0.365 of a milliamp. So that's actually 0.000365, okay? And so a very, very small amount of current. Now what I'm going to do is I'm going to take right away and I'm going to multiply that by the gain, because I know that my collector current will be 120 times greater than that. So times 120. and I'm looking at 43.8 milliamps. So this current here going this way, 43.8 milliamps. Okay, now how do I find resistance when I know voltage and current? So R is E over I. So we want 31.9, and we want to divide it by the 43.8 milliamps, and it looks to me like the answer is 728 ohms. 728 ohms. So this resistor right here, 728 ohms. That's the load resistance. And if you think about it, in order to have 31.9 volts, it's a very, very small current, but that looks about right. Large resistors, larger voltage drops, and but totally calculatable as long as we can come up with this. Now, the thing that makes this predictable is the fact that we know the exact ratio between this current and this current, 120 times difference. Okay, and so that's the way that we can kind of solve that. A little bit different variables, right? Just different variables. Okay, I want to do one more example in the linear state. Okay, and so linear now, we're talking about active. We're going to be somewhere in between saturation and cutoff. So I'm going to take a couple moments. I'm going to start a little bit of a skeleton drawing, and then we'll fill it in. So I'm turning now to a different state, and so I want to do an example of the transistor in its linear or active state. And so I've given you a source voltage 12 volts, and this transistor has a beta of 250 times. So that means that the collector current will be 250 times larger than the base current. Now, if we're in the active zone somewhere, that means that the load voltage, the load voltage, if it's cut off, would be 0 volts. And the load voltage at saturation would be 11.9 volts. And so what you can see is what's given here is a 6 volt load voltage. So we're in that stage where we're kind of amplifying the base signal, the base current, and we're somewhere in between. And so what we want to say is how much resistance would we have in the base resistor in order to bring us to this condition, this state that we're in. And so I want to just put in some voltage information that we can deduct from what we know about these circuits. Remember, this is our load circuit down here, and these two voltages, VCE and V of the load, VRL, have to equal 12 volts. That means VCE equals 6 volts. Okay, so we're at a half and half point there. Now, as long as we're conducting, we know that this is 0.7 of a volt from B to E, and that means that we have 11.3 volts on our actual base resistor. Now, let's take a look at what information we have that we can deduct here. Looks to me like the place where we have all, enough values to actually do some calculations are down here at our 16 ohm load and our 6 volt voltage. And so we know what it is that actually changes is the voltage goes up and down based on the collector current that's rising and falling in that load. So if I wanted to find the current, I will take the 6 volts, divide by the 16 ohms, and my current is 375 milliamps at this particular point. So I'm going to put 375 milliamps, 375. Now this current is 250 times larger than the base current. So if I divide by 250, I get a current here of 0.0 0.015, which is actually 1.5 milliamps. Okay, 1.5 milliamps. And in order to actually find, how much resistance that is, I just need to divide the voltage. So R is E over I, so divide the voltage by that very small current. So I'm just going to do that. And I think that I'm looking at 7,533 ohms. 7,533 ohms. And so interestingly enough, that's the number of ohms that it takes to essentially bring my load voltage to about 50%. The state that we're in here is active, but I do want to talk about for just a brief moment. If we wanted to bring this from this point and we wanted to raise this voltage to its highest point, we would need more current here, which would mean we would need more base current. So what would we need to do? We would need to reduce this resistance. So this would literally have to be a variable resistor, and we would have to reduce the resistance, which would raise this base current, which would raise the collector current until, and the highest we could go would be 11.9 volts. And so I'm not going to run that one through. I'd like you to do the math on it though, and you can just double check this. I've done a couple of calculations. The resistance that is necessary to bring this to saturation, and I'd like you to double check this, but you can do that after when you have a moment. So the resistance to bring this circuit to saturation should be about 3,798 ohms, okay? So what you're seeing here is we would actually reduce this resistance down to 3,798, which would raise this current, and we would be sitting at 11.9 volts and 0.1 of a volt VCE, and we would call that saturation. So just so you see where we would go with that. Right now we're in the active linear state. That would take us to saturation.